Okay, so my presentation, I almost feel like I want to say, well, the first example is fairly stupid, but it's a very practical example. And I'll start with some case studies. This is what I consider as the basics. So first of all, the flow sheets. Does the unit processes integrate properly in the total flow sheet? Experience. What are the tricks that the experienced people have learned over the years on specific equipment and processes? And I think as a young metallurgist, it's you sort of obliged to go and speak to the, if we can call them the elders, and maybe share some history. What has gone wrong? Where? How did they fix it? You know, learn through their experience. I think it's a very important factor. Then communication. Does the right information get passed to the operational employees? And what do I mean with this? A lot of the times, for example, sampling. Our metallurgists obviously get their results and they know what the efficiency curves mean, whatever the sampling campaign is all about, but it doesn't necessarily get shared with the operational people. And I think this is an important factor. Once the operational people, for example, if we show them an efficiency curve for a cyclone and explain to them how it works, they will actually start understanding the operation better and it will be beneficial to the plant operations. Okay, next one, best practice, basic process fundamentals and best practices. I think on most of our products during our training as well, Adams will cover some of it. We've got specific best practices on some, let's say, for example, the DMS operation. Then this is a very important question. What's changed? What changes have been made to your plant and why? So when you get to a new plant, or maybe you get moved around from a gold plant to a platinum plant or whatever the case might be, is to look at the history of the plant, the changes that they've made and why they've made those changes. And there's obviously a good chance that they've made it because the mineralogy of the ore has changed or whatever the case might be. Then maintenance. Are the mechanical aspects of your equipment in a required state? And you'll see what I mean with that when I get to the flotation parts. Okay, so my first case study was one of my gold customers. And as I arrived there on a routine visit, he said, well, hop into my vehicle. We're going to take a drive around the various sites that they're mining, the old slime dams. And if you see anything, you know, just tell me or inform me what you think we could possibly improve or change. And the first screen we got to was a typical linear vibrating screen. It had 5mm slotted apertures on it. And I got on to the side of the screen, I had a look on the screen, and it was running perfectly. There was nothing wrong. The bed depth was correct. Everything looked fine. And if I now got into the vehicle and driven off of the plant manager to the next side, I wouldn't have this case study. And that's what I'm trying to get to now. So my question was, okay, so what do you do with this +5 material? Now we dump it. Okay, so the -5 material, okay, that gets pumped 3 kilometers to the plant where it first gets screened on a 2mm linear screen. Okay, so my next question obviously is, okay, so what do you do with the oversize and the -2 from the linear screen? So the oversize, that gets loaded by trucks periodically and then gets dumped back on the original mine site. The -2 material, that actually goes into the plant. Now, I'm going to ask our viewers or participants to maybe quickly make a comment in our chat box. What do you think is wrong with this picture? And I'm going to give you a couple of seconds to think about it. I don't see any comments yet in our chat box. Okay. So my question to the plant manager was, the following. So if you're taking out the +2 material at the plant, why are you not using a 2mm aperture right in front at this first screen where we are now? And he looked at me and admitted that he was slightly embarrassed, and he said, well, you know what, I've been here 8 years and I've never actually thought about it. And that is the thing. Sometimes we miss small, little, almost stupid little things. So what happened, we then changed the first screen with the 5mm apertures. We changed that aperture to a 2mm aperture. And the result of that was that there was no more +2 oversize that could be transported by those trucks because it's been screened out at this primary screen already. So why am I showing you? What has this got to do with the topic of this webinar? The fact is they saved 75,000 Rand per month by cancelling the truck, the contractor, for trucking the material away because there wasn't any material to truck away anymore. And it was just because of a simple observation. Right, the next little case study is a coke screen application. It's an iron ore smelting plant. The coke screens are just ahead of the blast furnace, obviously feeding material as a blend into the blast furnace. The customer was experiencing challenges of excessive pegging on the coke screen, and you'll see a picture of the screen in the following slide. Now the coking material they are very ugly shaped particles, and when they're not quenched properly, they slightly over what they're supposed to be temperature, and it tends to burn the material. So we get a combination of pegging and where this material actually sort of burns into the screen media. So what happened, and this is where I'm going to go to the next slide to show you what the screen looks like. If you look at the screen, you'll see that crossbar going over there. On the feed section, that is the panels that we had then gone on to design, and it's called a vibro hex panel. It's got a hexagonal shape and we've got a slot between the apertures. On the discharge side, this is our oppositions panels, round apertures, and as you can see, there is almost no apertures that are left open. All of them are pegged, so very little was actually happening within that screen. And after we tested our panels on the feed end, obviously they worked very well, and we then replaced the rest of the deck with the hexagonal type panels. Now, before you start thinking that this guy is trying to show the whole world how clever he is, let me show you how easy it is to actually make a boo-boo. After the success of these panels that I used on the specific screen, I had another application where ferrochrome ore. They crush it and then screen it, and I had exactly the same problem as we see on the discharge side of the screen. The material also very irregularly shaped, terrible shapes, and I then went and I convinced the customer that I had a solution for his problem. So we installed the hexagonal, the panels at the manganese or the ferrochrome plant, and guess what happened? After 5 days, those panels failed dismally. Now, why would that be? And the answer is this. The density of that ferrochrome material is almost 3 times the density of the typical sinter material. So the load onto those panels are significantly higher than on this sinter screen. And what happened? The frames actually failed, the panels dished, and that is, if I can show you with my hand, what happens is when they dish, they actually bend under load. And that cost Multotec money, and it wasted some of the production time on that plant. So a simple assumption that because they worked, they're now going to work on a different plant, you've got to be very careful. Each application is very specific, and you've got to think about all of the factors that are involved. Okay, now to screen decks. Just to show you what our guys or our team in Australia is doing. I think it's a slightly different ball game down under. Some of those plants treat very high tonnages, and what our teams had to do over there is to give the guys a solution for or to extend the life of their panels. And these deck maps show the different configurations of different types of panels that we use in different areas on the screen deck. And we can have up to 14 different types of panels, and I'm going to show you some examples of what they would look like, the different types that we could use on one screen. I also now want to show you why I'm showing you the specific deck map and the importance of it. So 2 examples from our Australian team. They had a scalping application where the competition's panels weighed 58 kgs. The typical life was 6 weeks, then the panels were done, finished. And our team then went and redesigned the panels. They made them lighter, and they increased or they doubled the life. Now, so what was the result of that? Well, ultimately, the plant could produce, by reducing the downtime, by replacing the panels, they had an increase of 1.5 million tons per annum. And the screen media savings on that specific plant was $634,000 per annum, which is significant. And the 1.5 million tons that I said they could now produce more ore was worth $112 million per annum. Another example, and this ties in with Gulf's presentation as well in terms of field maintenance. The impact panels on a screen, they also had problems with the specific area because a wet scrubber was feeding 300mm material with a drop of 3 meters. So obviously you're going to have excessive wear on the feed area, especially if it's iron ore. Now our competitors' panels in that specific application, sorry about that, they were lasting 2 to 4 weeks. Our Australian team designed new panels for that specific feed section, and they got a life between 12 and 14 weeks, obviously reducing the downtime for the replacement of these panels. Now, what was that worth? The total savings in that specific case, including the cost per shutdown, was $344,000 per annum. Okay, another little case study. One of my diamond customers, he actually called me and said that I must come and have a look. He's got a problem. So what happens on this screen, the top deck has got a 12mm aperture right through. The oversize from the top deck, that gets discarded, he throws it away. The -12 or -10, that will be the cut point on the top deck. That bottom deck oversize also gets discarded. Why? Because there's no diamonds. He's actually going for the -4mm particles, which carries the diamonds in that specific area. So the undersize from the bottom deck is the product that actually goes to the X-ray sorters. Now, his problem was the following. He was losing diamonds in the bottom deck overside in that discard. And he said, okay, you guys are the screening experts. You solve this problem. I'm not going to buy a new screen. Don't tell me it's under capacity or whatever the story is. I want you to solve it. And I had to think about this for a while, and then there is a certain pattern or profile on any screening material. And typically you can divide that screen into 3 different sections: the feed part, the middle part, and then the discharge side. The feed end Initially, you will have a lot of material with a thick bed where the smaller particles are struggling to get through. And as they start going through, your middle section will have an increased bed depth as the undersize now starts going through that screen deck. And then finally on your third section, you will have most of your near size that hasn't been screened through. They will then typically go through on the discharge end in that third area. And what I did was I changed the apertures. The first part of the screen I changed to a 14mm aperture. Then, I just want to check. The second part, I actually reduced the aperture from 12 to 10. And then the third part, the last discharge section, I kept exactly the same aperture. And what that did, it actually took that profile and it made it more constant on the bottom deck. And the result of that exercise was that when we made those changes, there was no -4 material in that discard anymore. He was not losing any diamonds anymore. Now this, like I said just now, it's a very specific application. I would have not been able to do that if this discard material wasn't discard and it was indeed a feed or a product going to a next operation where the size was important. Because if I start changing the apertures, I start changing the PSD of that oversize on the top deck. And the same applies to the bottom deck. If there was a process, a next process where those particles were supposed to go to, I wouldn't have been able to make that change. So very application specific. This change was less than 25,000 Rand to change those panels, and this customer was certainly very happy after this change. And as the saying goes, happy wife, happy life. And in this case, or for us, happy customer equals Multotec salary at the end of the month. That is our job, to keep our customers happy and to add value. Okay, so for flotation, I'm just going to read through my comments there. Flotation circuits typically require special attention and operational care. I think most of us are aware of that. What can be done before one focuses on the mineralogy, chemistry, and operational control aspects? So in other words, you've got a flotation plant. You get to this plant, let's say you've been transferred from another plant, and where do you start? What can you do? And I'm going to use an ex-employee of Multotec that actually went back into the platinum industry as an example. So what he did, he started off by taking each flotation cell offline, cleaning it out, taking out all of the rubbish that is settled in the bottom of that cell, thereby increasing the volume of that cell and thereby also increasing the retention time, because less the volume, less the retention time of the slurry within that cell. And systematically over a period of around 4 months, he replaced all of the parts that were not up to the design criteria, or they were not on spec. And ultimately, after that exercise, he increased the recovery of the flotation circuit with 3%. Now in platinum, that is significant. It's a hell of a lot of money. So sometimes you've got to spend a little and then you get the advantage of those expenditures by way of increasing the efficiency of the process. And that's the end